Have you ever looked up at the night sky and felt like there's something more, something hidden just beyond our grasp? The universe has a way of whispering secrets through the stars, leaving clues in the way galaxies spin, the way black holes hum, even in the way light bends across the cosmos. For centuries, scientists and dreamers alike have chased these patterns, trying to crack the code of existence itself, and what they've discovered might just rewrite everything we thought we knew. This isn't just about distant planets or swirling nebulae, it's about the invisible threads stitching reality together. Think of the universe as a grand puzzle, where every piece fits in ways we're only beginning to understand. Some of these hidden patterns defy logic, bending the rules of physics as we know them. Others hint at dimensions beyond our own, or forces so subtle they've eluded detection for millennia. And the wildest part, many of these theories aren't science fiction, they're real, cutting-edge ideas being explored by some of the brightest minds on Earth. That's exactly what we're diving into today, 30 mind-blowing theories about the universe's hidden patterns. From the strange symmetry of quantum particles to the eerie echoes of parallel worlds, we'll uncover the mysteries that keep astronomers awake at night. Some of these ideas will challenge your sense of reality. Others might make you question whether we're truly alone in the cosmos. But one thing's for sure, by the end of this journey, you'll never look at the night sky the same way again. So settle in, because the universe is about to reveal its deepest, most astonishing secrets. What if the universe has a favorite number? Look closely, and you'll find it everywhere, from the curl of a seashell to the whirl of a hurricane. But here's where it gets cosmic. The same spirals that shape life on Earth also sculpt galaxies millions of light years away. This isn't just random artistry, it's the Fibonacci sequence, a mathematical rhythm where each number is the sum of the two before it. 0, 1, 1, 2, 3, 5, 8, and on into infinity. Take a spiral galaxy like the Milky Way. Its arms don't twist haphazardly, they unfurl with near-perfect Fibonacci precision, echoing the same logarithmic spiral found in sunflower seeds or pine cones. Even the orbits of planets and moons sometimes dance to this numerical tune, with ratios between their distances matching Fibonacci numbers. It's as if the universe sketched these patterns with the same geometric pen. But why? Some scientists argue it's simply nature's most efficient way to pack matter tightly while allowing growth, like a cosmic origami fold. Others whisper about something deeper, a hidden language of energy and vibration, where gravity and quantum forces play by Fibonacci rules we're only beginning to decode. Whether it's pure math or a fingerprint of something grander, one thing's certain: the cosmos has a flair for Fibonacci, and that might just be the first clue in a much larger mystery. Now picture this: a faint glow fills the entire universe, lingering like an echo from the moment of creation itself. This is the cosmic microwave background, the oldest light we can observe, a snapshot of the infant cosmos just 380,000 years after the Big Bang. But here's where things get strange. Instead of being perfectly uniform like a smooth blanket of radiation, it's littered with bizarre anomalies. Some regions are oddly colder than they should be. Others show peculiar asymmetries, as if the universe was stitched together unevenly. Take the so-called cold spot, a mysterious region in the southern sky where temperatures dip dramatically compared to surrounding areas. At first glance, it might seem like a cosmic hiccup, but its scale is staggering, spanning nearly 2 billion light-years. One explanation: it could be the ghostly imprint of a collision with another universe. That's right, some physicists speculate this cold patch might be a bruise left behind when our universe brushed against a parallel one in the multiverse. Imagine two soap bubbles grazing each other in a cosmic foam, leaving faint fingerprints where they touched. Then there's the even wilder possibility: these irregularities might be scars from a time before the Big Bang. Certain theories suggest our universe wasn't born from nothing. but emerged from the collapse of a previous cosmos like a phoenix rising from the ashes. If that's true, the cold spot and other asymmetries could be cosmic leftovers, fragments of a forgotten cycle encoded in the universe's first light. Of course, skeptics argue these are just statistical flukes, cosmic static with no deeper meaning. But what if they're not? What if these whispers in the microwave background are the first tangible clues pointing to realities beyond our own? The hunt for answers has only just begun, and with every new telescope, we're peeling back another layer of this ancient, enigmatic message from the dawn of time. Imagine a solar system where planets don't just orbit randomly but move in perfect mathematical harmony. Their distances from the Sun following an ancient ratio found in art, architecture, and even our own bodies. This is the golden ratio, approximately 1.618, a number so precise it's been called the fingerprint of the gods, and it doesn't just appear in human designs. Stretch a tape measure across our solar system, and you might spot it hidden in plain sight. Take Venus and Earth, for example. The time it takes Venus to orbit the Sun, about 225 days, compared to Earth's 365 days, forms a ratio eerily close to the golden number. Even more striking, the arrangement of Jupiter's moons follows a similar pattern. Io, Europa, and Ganymede, three of its largest satellites, complete their orbits in a rhythmic dance where the timing between their alignments mirrors the golden ratio almost exactly. It's as if some invisible hand tuned their movements like celestial clockwork. But is this a cosmic coincidence or something deeper? Skeptics argue that with countless planets and moons in the universe, a few are bound to align with the golden ratio purely by chance. Yet others point out how often this ratio emerges not just in orbital mechanics, but in the spiral arms of galaxies, the branching of trees, even the proportions of our DNA. Could it be a universal blueprint, a mathematical constant woven into the fabric of space itself? Here's where the mystery deepens. Some researchers propose that the golden ratio isn't just a pretty pattern. It might be nature's most stable configuration. In orbital dynamics, certain ratios minimize gravitational tugs, reducing chaos over billions of years. Planets or moons locked into golden ratio orbits could endure longer, avoiding catastrophic collisions or ejections into deep space. If true, this wouldn't just explain why we find the ratio in our solar system, it might reveal why life-friendly systems like ours exist at all. Then there's the radical idea that the golden ratio isn't just a passive result of physics but an active force. A handful of theorists speculate about resonant fields or vibrations threading through the cosmos, subtly shaping matter and motion into golden proportions. It's a fringe notion, but if even partially true, it would mean the universe isn't just governed by equations, it might be singing them. So next time you gaze at the night sky, remember, those silent, gliding planets might be more than rocks and gas. They could be traces of a hidden melody, a rhythm written into the stars, one we're only beginning to hear. Zoom out far enough and the universe reveals a secret, one written in the clustering of galaxies across unimaginable distances. At first glance, these glowing islands of stars seem scattered randomly, like paint flicked across a dark canvas. But pull back further and a breathtaking pattern emerges. Vast filaments of galaxies stretching billions of light years, connected in a web so intricate it resembles the branching veins of a leaf or the delicate frost on a winter window. This isn't just cosmic coincidence, it's a fractal, a shape that repeats itself at every scale, from the tiniest snowflake to the grandest superclusters in existence. The evidence is everywhere. Measure the distribution of galaxies and you'll find clusters within clusters, filaments within filaments, all echoing the same mathematical rhythm. The Sloan Digital Sky Survey, one of the most detailed maps of the cosmos ever made, shows this fractal-like structure with startling clarity. Giant walls of galaxies like the Sloan Great Wall, stretching over 1 billion light-years, aren't solitary anomalies. They're part of a repeating script, a cosmic code where the universe rebuilds its architecture in increasingly larger copies of itself. But why would the cosmos favor fractals? One compelling answer lies in the echoes of the Big Bang. In those first moments, infinitesimal quantum fluctuations, tiny ripples in the fabric of spacetime, were stretched to cosmic proportions by rapid expansion. Gravity then sculpted these ripples into the web we see today, amplifying the fractal pattern with every passing eon. It's as if the universe took a single mathematical whisper and blew it up to galactic scales. Yet not everyone agrees. Some astrophysicists argue the fractal nature breaks down at the largest scales, giving way to a smoother, more uniform distribution, a concept called the end of greatness. Others propose something far stranger, that fractal patterns aren't just relics of the Big Bang but signatures of an underlying physics we've yet to discover. Could gravity alone explain these intricate formations, or is there a hidden force, a cosmic glue orchestrating this grand design? Then there's the mind-bending implication. If the universe truly is fractal, it might mean the cosmos is infinite in a way we've never imagined. Not just endless in space, but endlessly detailed, with structures repeating ad infinitum. Picture a universe where every galaxy cluster contains smaller versions of itself, and every filament branches into tinier filaments down to scales we can't even observe. It's a hall of mirrors stretching beyond the observable horizon, challenging our very notions of beginnings and endings. Whether fractal or not, one thing's clear: the universe's large-scale structure isn't random. It's a fingerprint, a clue left behind by the forces that shaped reality itself. And as we map deeper into the cosmic web, we might just find that the patterns we're tracing aren't merely features of the universe, but a message from its very foundations. What if everything we see, every star, every planet, even the space between them, is nothing more than an illusion, a cosmic mirage painted onto the fabric of reality itself? This isn't the plot of a sci-fi movie, it's the holographic principle, one of the most radical ideas in modern physics. Imagine the universe as a movie screen, projecting a three-dimensional world from information etched on a flat, two-dimensional surface. Sound impossible? Let's break it down. The theory traces back to an unexpected place: black holes. When scientists calculated how much information a black hole could contain, they hit a paradox. According to quantum mechanics, information can't be destroyed, but if matter falls into a black hole, it seemingly vanishes forever. The solution: maybe the information isn't lost. Instead, it could be smeared across the black hole's event horizon, the point of no return, like data encoded on the surface of a DVD. Here's the twist: if this works for black holes, why not the entire universe? Think of it like this: hold up a credit card hologram, tilt it, and a 3D image appears, even though the data is stored on a flat, shiny sticker. The holographic principle suggests reality works the same way. The three-dimensional cosmos we experience, the depth of space, the swirl of galaxies, might just be a projection from a two-dimensional boundary at the edge of the universe. Every particle, every force, every ripple of gravity could be bits of information written on this cosmic ledger, with our perception filling in the third dimension like a neurological trick. But how could this possibly be true? The math points to something startling. In the 90s, physicists discovered that the equations describing events inside a volume of space match perfectly with those describing events on its surface. It's as if the universe is performing a sleight of hand, hiding its true, flat nature behind the curtain of our senses. Even stranger, this might explain why the universe seems pixelated at the tiniest scales. Just as a digital image breaks into grainy dots when zoomed in too far, space-time itself might be made of indivisible bits, with the holographic principle acting as the ultimate compression algorithm. Skeptics argue this is all theoretical gymnastics after all. We can't exactly peek behind the universe's projector screen, yet there are tantalizing clues. Some versions of string theory, a framework attempting to unify all forces of nature, rely on holographic math to make their equations work. Meanwhile, experiments with ultra-precise gravity wave detectors might one day uncover faint noise in space-time potential static from the universe's hidden 2D code. If proven true, the implications would rewrite reality as we know it. Time, distance, even causality might not be fundamental, just emergent properties of a deeper, flatter truth. It would mean you, me, and everything we've ever known are shadows dancing on the walls of a higher dimensional cave, and that raises the most haunting question of all. If the universe is a hologram, who or what is holding the projector? Imagine floating alone in an endless void, no stars, no planets, just infinite darkness. Now picture this: out of the chaos, atoms suddenly collide in just the right way, forming a brain. Not just any brain, but one identical to yours, complete with all your memories, thoughts, even the sensation of reading these words right now. It exists for just a moment before dissolving back into the abyss, utterly convinced it had a life, a world, a history that never truly existed. This isn't a nightmare, it's the Boltzmann Brain paradox, a thought experiment so unsettling it makes scientists question whether we're even real. The idea comes from thermodynamics, specifically Ludwig Boltzmann's work on entropy, the tendency of the universe toward disorder. In an infinite cosmos, even the most improbable events must happen eventually, given enough time. Spontaneous fluctuations could, in theory, assemble complex structures like conscious minds from pure randomness. The shocking implication: if the universe lasts long enough, Boltzmann Brain's self-aware entities conjured from chaos should vastly outnumber naturally evolved beings like us. Statistically, you are more likely to be one of these fleeting illusions than an actual person in a stable universe. But why hasn't this happened yet? After all, assembling a single brain by accident seems easier than crafting an entire 8-billion-year-old cosmos with galaxies, planets, and life. Some physicists argue this paradox undermines our assumptions about reality. If Boltzmann brains are inevitable, how can we trust our memories or observations? The coffee cup in your hand, the device you're watching this on, all could be phantom impressions from a momentary blip in the void. Not everyone buys into this existential horror. Critics point out that for every Boltzmann brain forming, an unfathomable number of disordered configurations would dominate. The odds of a fully functional, self-aware mind popping into existence are so vanishingly small that even infinity might not guarantee it. Others propose that the very laws preventing such spontaneous consciousness, like quantum decoherence, act as cosmic safeguards, ensuring only stable, coherent realities persist. Yet the puzzle lingers, forcing us to confront profound questions. Is the universe fine-tuned to prevent such aberrations, or are we somehow immune to them by virtue of existing? Could the paradox hint at deeper flaws in our understanding of time, entropy, or even consciousness itself? The chilling possibility remains. In an eternity of chaos, the line between reality and illusion might be thinner than we dare admit. Ever questioned the fabric of your reality? What if every star in the sky, every law of physics, even the thoughts in your mind weren't fundamental truths but lines of code in an unfathomably advanced simulation? This is the simulation hypothesis, a theory that's moved from fringe philosophy to serious scientific debate, and the clues might be hiding in plain sight. Start with quantum mechanics, where particles defy logic by existing in multiple states at once until observed, as if the universe is optimizing processing power by only rendering reality when needed. Then there's the uncanny precision of mathematical constants. Gravity, the speed of light, the charge of an electron. Tweak any of these values slightly, and life as we know it collapses. Such fine-tuning feels less like cosmic luck and more like deliberate parameters set by a programmer. Even the pixelated nature of spacetime at the tiniest scales, where reality breaks into indivisible Planck-length units, hints at a grid-like substrate beneath the illusion of continuity. But who could build such a simulation? Imagine a civilization millions of years ahead of us, with computational power dwarfing all Earth's resources combined. If they could simulate conscious beings even as imperfect copies statistically, the number of artificial minds would vastly outnumber organic ones. This raises a chilling corollary. The odds with the original, base reality are vanishingly small. Critics argue that simulating every atom in a universe would require impossible energy. Yet proponents counter that advanced beings might use shortcuts, like only simulating conscious observers or approximating unobserved regions. After all, video games don't render entire worlds at once. They generate details as players approach. Could cosmic rays or quantum glitches be the equivalent of rendering errors in our universe's code? The simulation hypothesis isn't just speculative fun, it reshapes how we view existence itself. If true, it turns science into reverse engineering, philosophy into debugging, and the search for extraterrestrial life into a hunt for the system administrators. Until we find definitive proof or a cosmic blue screen, the question lingers: are we explorers of the universe or merely characters in its grandest story? Deep within the abstract world of mathematics lies a number system so peculiar. Most physicists avoid it entirely, yet it might hold the key to unlocking the universe's deepest symmetries. Meet the octonions, an 8-dimensional numerical oddity where even basic arithmetic defies intuition. Unlike the numbers we use daily, multiplying octonions isn't just about quantity. It's a dance where the order of operations changes the outcome, like twisting a Rubik's Cube that reshuffles itself with every turn. At first glance, this seems like mathematical esoterica, but zoom in, and you'll find octonions lurking in the equations of string theory, whispering secrets about reality's hidden architecture. String theory, the ambitious framework aiming to unify all forces of nature, suggests the universe isn't made of point-like particles but vibrating strings. To work, these strings need 10 dimensions, 6 of which are curled up too small to detect. Here's where octonions enter the stage. Their unusual properties perfectly mirror the geometric twists and folds required to compactify these extra dimensions. Think of it like fitting an elaborate origami sculpture into a thimble. Octonions provide the crease patterns that prevent the math from tearing apart. But the connection runs deeper. The standard model of particle physics classifies fundamental particles using symmetries called Lie groups. Octonions, with their intricate rotational behaviors, generate a rare Lie group known as E8, a structure so vast it could catalog every known particle and force, plus ones we've yet to discover. It's as if nature's playbook was written in octonionic code, waiting for us to crack it. Why does this matter? Because octonions might solve string theory's biggest headache, its near-infinite possible solutions. Most versions of the theory predict a landscape of universes with different physical laws, making testable predictions impossible. But octonions impose constraints like a master key that only fits certain locks. If correct, they'd filter out nonsense universes, leaving only those compatible with life as we know it. Skeptics caution that octonions are too abstract to map onto reality. After all, no other field of physics relies on such exotic math. Yet history shows breakthroughs often begin with dismissed curiosities. Imaginary numbers, once deemed useless, now underpin quantum mechanics. Whether octonions are a stepping stone or a dead end, one thing's certain. In the quest for a theory of everything, the universe keeps pointing to patterns far stranger than fiction. Somewhere in the depths of space, the cosmos might be playing a trick on us, one so bizarre it's been dubbed the axis of evil. This isn't the plot of a sci-fi thriller. It's a real, unsolved mystery in modern cosmology. Picture the cosmic microwave background, that ancient afterglow of the Big Bang, as a celestial fingerprint. Scientists expected it to be uniform, like static on an old TV screen. Instead, they found something unsettling, a string of anomalies, cold spots, hot spots, strange asymmetries, all eerily aligned along a single axis stretching across the universe. It's as if the cosmos has a hidden equator, a line of cosmic longitude where the rules of physics seem to bend. The first clue came in 2003 when NASA Wilkinson Microwave Anisotropy Probe mapped the CMB with unprecedented precision. The data revealed a peculiar lopsidedness, a dipole, where one hemisphere of the sky was slightly warmer than the other. At first, scientists brushed it off as an artifact of our solar system's motion through space. But then, deeper analysis showed something worse. The quadrupole and octopole moments' finer details in the CMB's fluctuations were also aligned with this same axis. The odds of this happening by chance, less than 1 in 1,000. It's like rolling a die 100 times and getting the same number 90 of them. What could explain this? One possibility is that our universe isn't the smooth, isotropic expanse we thought. Instead, it might be fundamentally anisotropic, stretched or warped in a particular direction. Imagine blowing up a balloon with an invisible hand pressing on one side, distorting its expansion. Some theorists suggest this could hint at a pre-Big Bang structure, a relic of whatever existed before spacetime as we know it began. Others propose it's evidence of a neighboring universe exerting gravitational pull on ours, leaving a cosmic dent in the fabric of reality. Then there's the more radical idea. The axis of evil might be a flaw in our understanding of gravity itself. The standard model of cosmology relies on Einstein's theory of general relativity. But what if gravity behaves differently on the largest scales? Modified Newtonian dynamics, or MUND, offers one alternative, suggesting gravity strengthens where matter is sparse, potentially explaining the anomalies without invoking dark matter or cosmic defects. But even MUND struggles to account for the axis's precise alignment. Skeptics argue it's all a statistical fluke, an illusion created by our limited vantage point. After all, we're stuck inside the universe, peering out through the fog of galactic dust and foreground noise. Future telescopes, like the European Space Agency's Euclid mission, aim to test this by mapping the CMB with even finer resolution. If the axis persists, it could force a rewrite of cosmology's rulebook. The real enigma: if the axis of evil is real, it challenges the Copernican principle, the idea that Earth holds no special place in the universe. Finding a directional bias in the cosmos would mean, in some small way, we are aligned with a fundamental cosmic structure. Whether it's a glitch in reality's code or a shadow of something grander, one thing's clear: the universe still has secrets it's not ready to give up. And that's what makes the hunt so thrilling. At the heart of every black hole lies a paradox so profound it threatens to unravel our understanding of reality itself. The problem starts with a simple question. When matter vanishes beyond a black hole's event horizon, does the information it carried, the quantum states of every atom, every particle, disappear forever? According to Einstein's general relativity, the answer is yes. Black holes were thought to be cosmic shredders, crushing everything into a singularity where even the laws of physics break down. But quantum mechanics, the rulebook for the subatomic world, insists information can never be truly destroyed. It's like saying you could burn a library to ashes, yet somehow every word from every book still exists in the smoke. This clash isn't just academic, it strikes at the core of whether the universe operates on predictable, knowable rules. If black holes erase information, then reality is fundamentally unpredictable and quantum theory's foundation crumbles. But if information somehow escapes, then general relativity's portrait of black holes as inescapable prisons must be incomplete. For decades, this stalemate haunted physicists until a breakthrough emerged from an unlikely source: Hawking radiation. Stephen Hawking famously calculated that black holes aren't completely black. They emit faint radiation, slowly evaporating over eons. At first glance, this seemed to worsen the paradox. If the black hole vanishes, where does the swallowed information go? The answer might lie in the quantum fuzziness of the event horizon. Imagine the boundary not as a sharp line but as a seething quantum froth, where particles and antiparticles constantly blink in and out of existence. Occasionally, one escapes as Hawking radiation, carrying a scrambled imprint of the information inside. It's like a cosmic game of telephone where the message is fragmented but not lost. Recently, theorists have proposed even wilder solutions. The holographic principle suggests information isn't trapped inside but smeared across the black hole's surface, like a hologram encoding 3D data on a 2D screen. Others argue black holes might tunnel into baby universes, ferrying information elsewhere in the multiverse. And then there's the firewall hypothesis, the idea that the event horizon is a blazing wall of energy that vaporizes anything approaching it, preserving information at the cost of violating Einstein's vision of smooth spacetime. The implications ripple far beyond black holes. If information is preserved, even in scrambled form, it suggests the universe operates like a vast quantum computer, where every interaction is reversible and nothing is ever truly erased. Hidden in this paradox might be the blueprint for unifying gravity and quantum mechanics, a theory of everything. But if information is lost, we're forced to confront a cosmos where the rules we rely on are mere approximations, shadows of a deeper, stranger truth. One thing's certain, the black hole information paradox isn't just about what happens in the darkest corners of space. It's a mirror held up to reality itself, revealing how much we still don't understand and how much wilder the answers might be than we ever imagined. Step back and consider the sheer improbability of our existence. Every fundamental force, every constant woven into the fabric of reality, gravity's pull, the speed of light, the strength of atomic bonds, appears calibrated with razor-thin precision. Tweak any of these values even slightly, and the universe as we know it collapses. Stars wouldn't fuse hydrogen, carbon wouldn't form in stellar cores, and life's delicate chemistry would be impossible. This is the fine-tuning problem, and it's one of the most haunting riddles in modern science. Take the cosmological constant, which governs the expansion rate of the universe. If it were slightly stronger, galaxies would have ripped apart before life could emerge. Slightly weaker, and the cosmos would have collapsed back into a fiery crunch. The margin for error, 1 part in 10 to the power of 120, a number so absurdly small it's like hitting a bullseye on a dartboard the size of the observable universe blindfolded. Or examine the strong nuclear force which binds protons and neutrons together. Increase its strength by just 2% and stars would burn through their fuel in mere seconds. Decrease it by the same amount and complex atoms could never form. Even the ratio of electrons to protons is balanced on a knife's edge. A fractional difference and electromagnetism would overpower gravity, preventing galaxies from ever taking shape. So how do we explain this eerie precision? One camp argues for intelligent design, that these constants were deliberately set by some cosmic architect. But science prefers naturalistic answers, and here's where things get wild. The multiverse theory proposes our universe is just one bubble in an endless froth of realities, each with random physical laws. We simply inhabit the rare bubble where the numbers lined up right. It's like winning the cosmic lottery without realizing there are infinite losing tickets. Yet another possibility, these constants aren't fixed at all. Some theories suggest they could evolve over time or vary across space, with life emerging only in hospitable pockets. Others propose deeper laws might link these values, reducing the apparent fine-tuning to an inevitable outcome of undiscovered physics. The stakes couldn't be higher. If the multiverse is real, it reshapes our place in existence, rendering us a statistical fluke. If a deeper theory explains the tuning, it could unify physics as never before. And if the answer eludes us, well, that's the most thrilling possibility of all, proof that the universe still holds mysteries no one has even dreamed of yet. Picture two particles born together in a violent cosmic event, then flung to opposite ends of the galaxy. Despite the distance, they remain mysteriously linked. Change the spin of one, and its partner instantly flips too, as if sharing an invisible thread. This isn't science fiction, it's quantum entanglement, and its implications might stretch far beyond the lab. What if this bizarre connection isn't a rare quantum quirk, but the foundation of a vast, hidden network stitching the universe together? At the smallest scales, entanglement defies everything we know about space and time. Particles communicate faster than light, seemingly oblivious to the cosmic speed limit. Einstein famously called it spooky action at a distance, dismissing it as evidence of incomplete physics. But decades of experiments, from photons in labs to satellites beaming entangled particles across continents, confirm it's real. Now, some physicists wonder, could this phenomenon scale up? Imagine every star, planet, and atom linked by an imperceptible web of entanglement, a cosmic internet where information flows instantaneously. The math hints at something breathtaking. In quantum field theory, the vacuum of space isn't empty, it crackles with virtual particles constantly entangling and disentangling. Some researchers propose these fleeting connections might leave behind a persistent lattice, like frost forming delicate bridges between blades of grass. If true, the entire universe could be a tapestry of quantum links, with entanglement serving as the invisible glue holding realities seams together. This idea might even solve one of cosmology's greatest puzzles: how the early universe achieved such uniform temperature. The cosmic microwave background shows a near-perfect consistency across regions too distant to have ever interacted unless, somehow, they were once entangled. It's as if the Big Bang left behind a quantum handshake, synchronizing the cosmos at its birth. Skeptics argue that entanglement is too fragile to survive cosmic scales, decohering amid interstellar noise. Yet alternative theories suggest dark matter or undiscovered fields could stabilize the network, preserving quantum coherence across light years. Others point to black holes, where entanglement might thread through wormholes, weaving spacetime itself into a holographic pattern. The wildest implication: if entanglement connects everything, consciousness might not be confined to brains, but a ripple in the universe's quantum fabric. Far-fetched perhaps, but in a reality where particles chat across galaxies, the line between science and poetry blurs. One thing's certain: the universe's hidden threads are far stranger than we've dared to imagine. The universe has 1,000,000,000 secret, one so fundamental, it makes your very existence a statistical miracle. According to everything we know about particle physics, the Big Bang should have created equal amounts of matter and antimatter. Yet here we are, in a cosmos made almost entirely of matter, with antimatter vanishingly rare. This isn't just an oddity, it's the Barrian asymmetry problem, and solving it might reveal forces or symmetries we've never even imagined. Let's rewind to the beginning. When energy first crystallized into particles, every quark should have spawned an antiquark, every electron a positron. Matter and antimatter annihilate on contact, converting back to pure energy. So why didn't the universe cancel itself out instantly? The math suggests a tiny asymmetry, just one extra matter particle for every billion matter-antimatter pairs. That 1 in a billion surplus is all that survived annihilation, and it's the reason galaxies, planets, and you exist at all. Scientists call this imbalance charge parity violation, and it's been observed in certain rare particle decays. But here's the catch: known CP violating processes in the standard model account for less than 1/1,000,000th of the required asymmetry. That leaves a colossal gap in our understanding, pointing to undiscovered physics. Some theorists suspect hidden particles like sterile neutrinos or as yet undetected Higgs bosons that interact differently with matter and antimatter. Others propose that the asymmetry didn't arise in particle physics at all, but stems from cosmic inflation's quirks, imprinting a matter preference onto space-time itself. Then there's the wild card, primordial black holes. Recent models suggest these ancient relics, formed in the universe's first seconds, might have preferentially consumed antimatter due to subtle quantum effects. Imagine a cosmic scale coin flip where black holes acted as antimatter traps, leaving matter to dominate. The stakes couldn't be higher. If we uncover what tilted the scales, it wouldn't just explain why we're here, it could expose entirely new forces or dimensions. Experiments like the Deep Underground Neutrino experiment and CERN antimatter studies are hunting for clues. Every proton in your body is a fossil from that first asymmetry, a whisper from the dawn of time begging the question, was this imbalance an accident or the signature of something far grander? Galaxies aren't supposed to move like this. According to everything we know about cosmic expansion, matter in the universe should scatter randomly, like fragments from an explosion drifting apart in all directions. But in 2008, astronomers studying over 1,000 galaxy clusters made a spine-chilling discovery. These colossal structures were all streaming toward the same distant point in space, as if tugged by an invisible hand. This wasn't just a statistical fluke. It was a coordinated motion spanning billions of light years, defying the predictions of standard cosmology. They called it the dark flow, and it might be the first evidence of something beyond the edge of our observable universe pulling the strings. The data came from NAS, a Wilkinson microwave anisotropy probe, which tracked the motion of galaxy clusters by measuring the cosmic microwave background's subtle distortions, a phenomenon known as the kinematic Sunyaev-Zeldovich effect. As hot gas in these clusters interacts with CMB photons, it leaves a telltale imprint, revealing the cluster's velocity. To everyone's shock, hundreds of clusters showed identical directional movement at breakneck speeds, nearly 2 million miles per hour, toward a patch of sky between the constellations Centaurus and Vela. The kicker, this flow extended out to at least 3 billion light-years, far beyond the reach of any known gravitational force. So what could possibly exert such influence over structures so vast? One provocative explanation points to a gravitational anomaly outside our cosmic horizon, an unseen supervoid or even another universe bumping against ours in the multiverse. Imagine two soap bubbles floating in a bathtub. Where their surfaces nearly touch, gravity could leak between them, creating a phantom pull on our side. Alternatively, some theorists suggest the dark flow might be a relic scar from the Big Bang itself, a cosmic jet stream left behind when inflation slammed the brakes on the newborn universe's expansion. Skeptics counter that the dark flow could vanish with better data, a mere artifact of measurement errors or local galactic motions. But in 2013, the Planck satellite's more precise measurements threw gasoline on the fire. While it found weaker evidence for the flow than WMAP, it didn't rule it out entirely, and some analyses still suggest peculiar velocities aligning with the original findings. What makes the dark flow so tantalizing is what it implies about the limits of our knowledge. If real, it hints that the universe extends far beyond what we can see, with structures so massive they warp the fabric of reality on scales we can barely fathom. It challenges the cosmological principle, the notion that the universe is uniform everywhere, suggesting instead that we might live in a lopsided cosmic neighborhood, one suburb of a far grander metropolis we'll never glimpse. For now, the dark flow remains a shadow on the edge of understanding, a whisper of forces operating behind the curtain of space-time. Whether it's proof of parallel universes, a flaw in our gravity models, or just a cosmic mirage, one thing's certain: the universe still has moves we haven't even begun to decode. What if the Big Bang wasn't the beginning, just the latest chapter in an endless cosmic saga? The cyclic universe model flips the script on cosmology, suggesting our universe isn't a one-time event but part of an infinite loop of expansion and collapse. Picture a cosmic heartbeat, galaxies racing apart in a fiery Big Bang, only to reverse course billions of years later, pulled back by gravity into a cataclysmic Big Crunch. From that singularity, a new universe bursts forth, inheriting faint echoes of its predecessor's structure. It's not science fiction, it's a serious theory with roots stretching back to the 1920s, when physicists first toyed with the idea of an oscillating cosmos. The mechanics hinge on dark energy, that mysterious force accelerating the universe's expansion. In most models, dark energy ensures our fate is a cold, lonely fade into nothingness. But tweak its properties slightly and a different future emerges. If dark energy weakens over time, gravity could eventually gain the upper hand. Galaxies would slow their flight, then reverse, hurtling toward one another in a cosmic rewind. Matter and energy would compress until space-time itself fractures, rebounding in a new Big Bang. Some versions of the theory propose these cycles last trillions of years, each iteration subtly different from the last. Others suggest the cycles are near-perfect replicas, like a cosmic Groundhog Day where the universe repeats its patterns down to the atomic level. Evidence might already exist in the cosmic microwave background. Tiny anomalies, those unexplained cold spots and asymmetries, could be scars from a previous cycle, imprints of collisions between ancient universes long gone. Even the distribution of galaxies with their vast filamentary structures might reflect inherited templates from earlier cosmic incarnations. The math gets wilder. Some models eliminate the need for a singularity altogether, replacing the violent Big Bang with a smoother bounce where space contracts to a minimum density before springing back outward. But why believe in cycles? For one, it solves the fine-tuning problem. Instead of a single, improbable universe with perfect constants, cycles allow for trial and error. Countless iterations until conditions align for stars, planets, and life. It also dodges the thorny question of what came before the Big Bang by making time itself cyclical. There's no beginning or end, just an eternal rhythm of creation and destruction. Skeptics point to dark energy's stubborn persistence. It shows no signs of weakening. Others argue that entropy, the universe's tendency toward disorder, should accumulate across cycles, making each new universe messier than the last. Yet proponents counter that entropy might reset during the bounce, or that we're simply in a young cycle where order still dominates, the most tantalizing idea. If cycles are real, traces of past universes might linger in gravitational waves or quantum fields, waiting to be decoded. Future telescopes could hunt for concentric ripples in space-time cosmic fingerprints left by a universe that came before ours. Until then, the theory remains a breathtaking possibility that we're not the first universe and we won't be the last, just one note in an endless cosmic symphony. Zoom in far enough, past atoms, past quarks, past even the tiniest hypothetical strings, and you might hit the universe's ultimate resolution limit, the Planck length. At a mind-boggling 1.6 times 10 to the power of negative 35 meters, this isn't just another small measurement. It's the smallest possible distance that physics as we know it can describe, the point where space itself might stop being smooth and continuous and start looking more like a digital pixel grid. The Planck length isn't arbitrary. It's derived from nature's most fundamental constants: gravity, the speed of light, and quantum mechanics. Think of it as the universe's built-in minimum zoom. Go smaller and the math breaks down. Quantum fluctuations warp spacetime so violently that measuring anything below this scale would require so much energy, you'd accidentally create a black hole. It's like trying to measure the grooves on a vinyl record with a sledgehammer. You'll just smash the whole system. This raises a radical possibility. What if spacetime isn't an infinitely divisible fabric but a mosaic of discrete, indivisible tiles? Imagine reality as a cosmic image rendered in pixels too tiny for any microscope to see. Motion then wouldn't be seamless, it'd be a rapid flipbook of Planck-length snapshots, with existence updating its state in quantum jumps like frames in a film reel. Even time itself might tick in Planck-sized increments, roughly 10 to the power of negative 43 seconds apart. the implications ripple across physics. A pixelated universe could solve Zeno's ancient paradox, the idea that motion is impossible because you'd need infinite steps to cross any distance. With Planck units, there's a finite number of steps between points, making motion a series of quantum leaps rather than an infinite regress. It also offers a fresh angle on black hole entropy. The event horizon's surface area might literally count the number of Planck-scale pixels it contains, each holding a single bit of information, like a cosmic hard drive. But here's where it gets surreal. If space-time is quantized, our smooth, continuous reality is an illusion, a high-resolution approximation hiding its true blocky nature. Think of watching a sunset on a 4K screen. You don't see the pixels unless you press your nose to the glass. Similarly, Planck-scale granularity might only become obvious near black hole singularities or in the first instance after the Big Bang, where spacetime's underlying code is stretched to its limits. Not everyone's convinced. Some argue that a pixelated spacetime would distort high-energy light from distant gamma-ray bursts, smearing their arrival times, an effect we've never observed. Others propose alternative frameworks like loop quantum gravity, where space isn't made of pixels but woven from intersecting loops of quantum fields. Yet the allure remains. A digital universe resonates with the holographic principle, where reality's 3D complexity is projected from a 2D boundary. It even whispers to the simulation hypothesis: what if Planck lengths aren't just nature's pixels but literal bits in some unfathomable cosmic computer? Whether metaphor or mechanism, one thing's clear: at the smallest scales, reality might not play by the rules we're used to, and that changes everything. For centuries, the zodiacal light has haunted the pre-dawn and post-sunset skies, a ghostly pyramid of radiance stretching upward from the horizon, often mistaken for the first blush of morning or the last gasp of twilight. This ethereal glow comes from sunlight reflecting off cosmic dust scattered along the plane of our solar system, a shimmering river of particles left behind by comets and asteroid collisions. But here's the mystery. Ancient cultures didn't just observe this phenomenon, they wove it into their myths, rituals, and celestial maps with uncanny precision. Could they have glimpsed something in that subtle radiance that our telescopes and satellites have overlooked? Take the Babylonians, who meticulously tracked the zodiacal light's seasonal shifts, aligning their ziggurats to catch its glow during equinoxes. Or the Maya, whose Dresden Codex contains diagrams of a celestial serpent that modern researchers now suspect depicts the light's serpentine arc. Even the ancient Hindus described a sky bridge in the Vishnu Purana, its timing and position matching the zodiacal light's appearance in the tropics. These weren't just poetic flourishes. These cultures built entire calendars around these observations, suggesting they detected patterns or cycles invisible to the naked eye today. What secrets might they have unlocked? One tantalizing clue lies in the light's granular structure. Modern probes like NASA's Juno mission have revealed the zodiacal dust isn't uniformly distributed, it's clumped in strange, swirling filaments, possibly shaped by unseen planetary gravities or even interstellar magnetic fields. Ancient skywatchers, free from light pollution, might have perceived these subtle ripples as omens or celestial roadmaps. The Dogon people of Mali, for instance, described the zodiacal light as the path of the Nommo, associating its brightest knots with the orbits of invisible worlds, a striking parallel to contemporary theories about undiscovered Planet 9 perturbing distant dust clouds. Then there's the timing. The light's intensity fluctuates over decades, a rhythm modern science attributes to Jupiter's gravitational nudges on cometary debris. Yet Babylonian clay tablets record eclipse predictions that account for these variations centuries before Kepler's laws. How? Some researchers speculate they tracked the light's interaction with Venus's phases, using it as a natural celestial clock. Others propose they noticed correlations between the dust's brightness and climatic shifts, harvest cycles aligned to cosmic dust density in ways we're only beginning to analyze with satellite data. The most provocative theory, that the zodiacal light once appeared radically different. Ice core samples hint at a historic spike in interplanetary dust around 3,000 years ago, possibly from a giant asteroid breakup. If true, the glow ancient astronomers saw could have been far brighter, revealing structures now too faint for us to see, like shadows of lost planets or the spectral trails of vanished comets. Whether these patterns hold scientific weight or reside in the realm of archaeopoetry, one thing's certain: the zodiacal light is more than scattered sunlight. It's a cosmic palimpsest, its layers inscribed with lost knowledge we're only now learning to read. And somewhere in its glow, the whispers of the past still linger, waiting for the right observer to decode them. What if the key to unlocking the universe's deepest secrets isn't some esoteric equation, but a geometric shape so complex it took mathematicians nearly a century to map it? Meet the E8 Lie group, a dazzling 8-dimensional structure with 248 symmetries, resembling an intricate cosmic snowflake. To most of us, it's abstract math, but to physicist Garrett Lissy, it's something far grander: the missing blueprint that could unify all forces of nature into a single, elegant framework. His bold proposal that every particle and force in existence, from quarks to gravity, is just a different facet of this geometric masterpiece, vibrating in the hidden dimensions of reality. Lissy's theory hinges on a radical idea: the universe's fundamental building blocks might not be particles or strings, but mathematical symmetries. Picture E8 as a cosmic kaleidoscope, where every twist reveals a new particle or interaction. The standard model's menagerie of particles, electrons, neutrinos, gluons, all find precise placements on this shape's vertices, like jewels set into a grand tiara. Even gravity, traditionally the stubborn outsider in quantum theories, slots neatly into E8's architecture, as if Einstein's equations were just one stanza in a much larger symphony. The implications are staggering. If correct, E8 could explain why we have exactly 3 generations of matter particles, why certain forces have specific strengths, even why spacetime has 4 dimensions, all as inevitable consequences of geometry. It's like discovering the universe runs on a hidden operating system with E8 as its source code. But here's where things get divisive. Mainstream physics has met Lissy's work with equal parts fascination and skepticism. Critics argue that while E8 symmetries are mathematically beautiful, they don't yet predict new, testable phenomena, a gold standard in physics. Others point out technical hurdles, like explaining how the theory's abstract dimensions compactify into the familiar fabric of space-time. Even Lissy admits it's incomplete, calling it a work in progress rather than a finished theory. Yet the allure persists. E8 isn't just a random shape. It's the largest simple Lie group, a mathematical archetype so fundamental it appears in string theory, black hole entropy calculations, and even the geometry of quasicrystals. Some researchers quietly speculate that if Lissy's approach can be rigorously developed, it might offer a path to quantum gravity that's simpler and more visually intuitive than labyrinthine string theories. The most tantalizing possibility, E8 might be more than a tool for unification. It could be a window into the universe's true nature. Ancient philosophers believed the cosmos was built from geometric forms like the Platonic solids. Modern string theorists envision reality as tiny vibrating loops. But what if the answer lies in between, not particles or strings, but the symmetries that bind them? Whether Lissy's vision holds up or not, one thing's certain: the universe loves patterns, and E8 might just be its most dazzling one yet. Imagine a snowflake that never melts, not because it's frozen in place, but because it endlessly reinvents itself, moment after moment, cycling through its patterns not in space but in time. This isn't a metaphor, it's a time crystal, one of the strangest phases of matter ever discovered. Unlike ordinary crystals like diamonds or salt, whose atoms arrange themselves in repeating spatial patterns, time crystals break the mold by oscillating in predictable, repeating sequences without any energy input. It's as if you could wind up a clock once and watch it tick forever, never needing another turn of the key. The idea emerged in 2012 when Nobel laureate Frank Wilczek proposed a radical question. Could matter exhibit periodic order not just in space but in time? At first, the notion seemed to defy physics itself. The second law of thermodynamics insists that systems evolve toward equilibrium, settling into stillness like a cup of cooling coffee. Yet time crystals dance perpetually, resisting this fate. Picture a row of pendulums swinging in perfect sync, their rhythm locked even without being pushed, a kind of quantum choreography that never winds down. How is this possible? The magic lies in what physicists call broken time translation symmetry. Normally, the laws of physics work the same whether you're watching a system now or an hour from now. But time crystals spontaneously break this symmetry, choosing specific moments to repeat their patterns, like a cosmic metronome ticking at its own inherent frequency. Experiments in 2017 brought the theory to life, using chains of ytterbium ions or nitrogen vacancies in diamonds, all coaxed into this bizarre state with precisely tuned laser pulses. The ions didn't just respond to the lasers, they oscillated at fractions of the driving frequency, a telltale signature of time crystallinity. The implications ripple far beyond curiosity. Time crystals could revolutionize quantum computing, acting as error-resistant qubits that maintain coherence in noisy environments. Their unyielding rhythm might even hint at deeper physics. Some theorists speculate they could model exotic phenomena like perpetual motion in black hole horizons or the quantum behavior of spacetime itself. Yet skeptics caution that true time crystals, as originally envisioned, may be impossible in equilibrium systems, with current examples relying on external driving forces. What's undeniable is this: time crystals shatter our intuition about order and energy. They're not just a new material, they're a new way for matter to exist, threading the needle between motion and stasis, between the ephemeral and the eternal. And somewhere in their ticking lattices might lie clues to mysteries we've yet to even name. Hidden in the equations of cosmology lies a doomsday scenario so extreme, it makes black holes and supernovas seem like minor cosmic hiccups. This is phantom energy, a hypothetical form of dark energy that doesn't just accelerate the universe's expansion, but does so with a terrifying twist. Unlike ordinary dark energy, which pushes galaxies apart at a steady rate, phantom energy grows stronger over time. Imagine pressing your foot on a car's gas pedal, except the pedal keeps sinking deeper on its own, sending the engine toward infinite speed. Now picture that happening to spacetime itself. The math is chilling. If phantom energy exists, it would cause the expansion of the universe to escalate exponentially, eventually overcoming every force that holds matter together. First, galaxy clusters would rip apart as the space between them stretches faster than light can bridge the gap. Next, individual galaxies would disintegrate, stars torn from their orbits like beads scattering from a snapped necklace. Then, as the phantom field intensifies, solar systems would unravel, planets ripped from their suns with a violence beyond any supernova. But the horror show doesn't stop there. In the final stages, atoms themselves would be shredded apart, nuclei unable to withstand the spacetime stretching around them. Even the fabric of reality would rupture in a cataclysm cosmologists call the Big Rip, a violent end where not just matter, but the very laws of physics are torn asunder. What makes this more than sci-fi speculation? Phantom energy emerges naturally from certain solutions to Einstein's equations, particularly those where the dark energy equation of state dips below -1. Current observations can't yet rule out this possibility. The uncertainty in our measurements of dark energy's properties leaves the door open for this nightmare fuel. Some theorists even suggest phantom energy could explain anomalies in the cosmic microwave background, those eerie asymmetries we've spotted in the universe's oldest light. If those patterns trace back to phantom fields stirring in the cosmic dawn, they might be the first whispers of an apocalypse already in motion, yet there's a bizarre silver lining. If the universe is doomed to rip itself apart, the timeline might offer a perverse kind of comfort. Calculations suggest the Big Rip wouldn't occur for another 22 billion years or more, long after the last stars have burned out. For civilizations of the far future, the first warning signs might be cosmic voids growing emptier at an impossible rate, or distant galaxies winking out as their light can no longer outtrace the expansion. It's a death sentence written in the fading glow of an already ancient cosmos. Of course, not all physicists buy into this bleak vision. Critics argue that phantom energy violates energy conditions that prevent exotic, universe-breaking phenomena. Others propose alternative fates like the Big Crunch or heat death that lack the cinematic violence of the Big Rip but might align better with quantum gravity's rules. Then there's the radical idea that phantom energy isn't a cosmic executioner but a phase transition. Just as water can flash into steam under extreme heat, space-time might boil away into a new state under phantom energy's grip, birthing a fresh universe from the ashes of the old. Whether prophecy or mathematical ghost, the phantom energy scenario forces us to confront an unsettling truth. The universe's expansion isn't just a backdrop for cosmic events. It's an active player, one that could, under the right conditions, rewrite the rules of existence itself, and lurking in those equations might be the ultimate hidden pattern, not just how the universe lives, but how it dies. Imagine a universe where reality itself evolves, where the stable world we see isn't just a given, but the result of a hidden selection process, a cosmic survival of the fittest at the quantum level. This is the spine-tingling premise of quantum Darwinism, a theory that merges the unpredictability of quantum mechanics with the iterative refinement of natural selection. At its core, it suggests that the classical, predictable universe we experience isn't the only possible outcome of quantum laws. It's simply the one that's been selected because it's the most stable, the most resilient, the most capable of persisting long enough for us to observe it. Think of Schrödinger's famous cat trapped in a box where it's simultaneously alive and dead until someone looks inside. Quantum Darwinism offers a radical solution to this paradox. The cat's alive and dead states aren't equally likely to endure. Instead, the universe favors the version of events that can leave the most copies of itself in the environment, like footprints in wet concrete. A single photon bouncing off the cat's fur, a vibration in the air, even the warmth of its body all act as witnesses, redundantly recording the cat's state. Over time, the version of reality that's most efficiently observed by these tiny interactions wins out, while fragile superpositions fade away like whispers in a storm. This idea flips traditional quantum theory on its head. Instead of a conscious observer collapsing the wave function, a notion that's long troubled physicists' reality emerges through a natural, almost democratic process. Stable quantum states are the ones best at replicating their information into the surrounding environment, effectively broadcasting their existence to the universe. It's as if the cosmos runs a continuous audition, with quantum states competing for the starring role in what we call objective reality. The result, the world we perceive, isn't a random slice of quantum possibilities, it's the subset that's robust enough to leave an indelible mark. Evidence for this might lie in the eerie predictability of the macroscopic world. Why do we never see chairs in quantum superpositions, half here and half there? Quantum Darwinism argues it's because such fragile states can't consistently imprint themselves on their surroundings. A chair's position is reinforced by countless photons scattering off it, air molecules bumping against it, even the gravitational tug of every atom in the Earth, all working together to vote for a single, stable version of reality. The more a state is replicated in the environment, the more it resists decoherence, that blurring of quantum possibilities into classical certainty. Critics raise tough questions. If reality is a popularity contest among quantum states, who or what counts as the audience? Does the environment choose winners, or is this just another way to dress up the measurement problem? Some argue quantum Darwinism merely shifts the mystery rather than solving it. Yet proponents point to lab experiments where quantum systems seem to prefer states that correlate strongly with their surroundings, like particles aligning their spins to match the dominant magnetic field, as if naturally selecting the most stable configuration. The implications are staggering. If quantum Darwinism holds, it could redefine our understanding of consciousness, suggesting that the act of observation isn't special, it's just another form of environmental interaction, one link in a chain of cause and effect that stretches back to the Big Bang. It might even hint at why our universe seems so finely tuned for life. Only in a cosmos with the right physical constants could stable, observable structures emerge at all. Like a cosmic version of the anthropic principle, we see the universe we do because it's the one capable of seeing itself. Whether this theory unlocks the secrets of quantum mechanics or simply adds another layer to the mystery, one thing's clear: the line between physics and biology just got blurrier. Reality might not be a fixed stage, but a living, evolving process, sculpted by the same forces that shape galaxies, ecosystems, and perhaps even thought itself. And that raises a humbling possibility. The universe we perceive isn't just out there. It's the one that learned how to persist long enough for us to notice. Black holes dominate the cosmic horror genre with their endless appetite, trapping everything that crosses their event horizon, even light itself. But what if there's a cosmic counterpart, a celestial fire hose instead of a drain? Enter white holes, black holes' hypothetical twins, where nothing can enter and everything explodes outward in an unstoppable torrent. If black holes are the universe's trash compactors, white holes would be its particle accelerators, ejecting matter and energy at velocities that make supernova look sluggish. The math is just as mesmerizing as the concept. Einstein's equations allow for white holes as valid solutions, essentially black holes running backward in time. Picture a black hole's singularity, but instead of crushing matter into oblivion, it spews it out in a Big Bang-like eruption. Some theorists suggest gamma-ray bursts, those mysterious cosmic flashes brighter than a billion suns, could be white holes coughing up swallowed material from eons past. Others take it further, proposing that white holes aren't just explosions but entire universes in their infancy. In this radical view, every white hole could be the seed of a new cosmos, birthing space-time from the wreckage of another. Here's where relativity twists the knife. While black holes form from collapsing stars, white holes demand conditions so extreme they might only exist as relics of the early universe, or as echoes of black holes' distant futures. Loop quantum gravity, a framework aiming to reconcile Einstein's theories with quantum mechanics, suggests that when a black hole's evaporation via Hawking radiation reaches its final moments, it might rebound as a white hole. Instead of vanishing in a poof of particles, it would undergo a quantum bounce, like a compressed spring suddenly released. The result, a fleeting white hole flashing into existence, potentially recycling the black hole's contents back into the cosmos. Evidence remains elusive, but tantalizing hints linger. Astronomers have detected ultra-high energy cosmic rays, subatomic particles moving at near light speed with no clear source. Could these be white hole exhaust? Then there's the curious case of JB 060614, a gamma-ray burst that defied explanation. No supernova, no neutron star collision, just a sudden, brilliant flare fading as quickly as it appeared. Could it have been a white hole's death rattle? Skeptics counter that white holes violate thermodynamics' sacred second law. boldly assuming energy can reappear unscathed after being shredded by a black hole's gravity. Yet the allure persists. If white holes exist, they'd rewrite cosmic history, turning the universe into an infinite Matryoshka doll of nested realities. Each black hole's collapse might birth a new universe inside it, with its own laws and constants, while our own cosmos could, in turn, be the white hole offspring of some long-dead ancestor universe. It's a fractal vision of existence where beginnings and endings blur, and every singularity hides a potential rebirth. Until we spot one in the wild, white holes remain a dazzling what if, a reminder that the universe's strangest ideas often start as mathematical ghosts before stepping into the light. Neutrinos are the ultimate cosmic shape-shifters, particles so elusive they pass through entire planets like ghosts, yet bizarrely unstable in their identity. Born in the nuclear furnaces of stars or the violent decays of radioactive atoms, these phantom particles come in three flavors: electron, muon, and tau. But here's the twist: a neutrino born as one type can spontaneously transform into another mid-flight, morphing identities faster than a master of disguise. This phenomenon, called neutrino oscillation, isn't just a quirky subatomic foible, it's a window into physics beyond the standard model, possibly even hidden dimensions curled like invisible origami through space-time. The discovery began as a cosmic accounting error. When physicists tallied neutrinos streaming from the sun, they found only a third of the expected electron neutrinos. Either the sun's fusion processes were broken, unlikely for a star that's burned steadily for 4.6 billion years, or the particles themselves were playing tricks. Experiments like Japan's Super Kamiok and Canada's SNO finally cracked the case. Solar neutrinos weren't vanishing. They were oscillating into flavors our detectors couldn't initially see, like chameleons blending into unseen wavelengths. What drives this metamorphosis? The leading theory involves neutrino mass, a concept the standard model long considered taboo. Oscillations imply that neutrinos, though nearly massless, aren't completely weightless. But there's a catch. The masses required to explain the observed transformations don't align neatly with the standard model's predictions. It's as if the particles are whispering secrets about undiscovered physics. Some theorists propose sterile neutrinos, a hypothetical fourth flavor that interacts only via gravity, possibly bridging to dark matter. Others suggest the oscillations hint at extra dimensions, where neutrinos briefly tunnel into hidden realms before re-emerging as different flavors. The most tantalizing experiments involve artificial neutrino beams. At facilities like Fermilab, physicists fire concentrated neutrino pulses through hundreds of miles of Earth to distant detectors. The journey amplifies oscillations, revealing patterns that would be imperceptible over shorter distances. Already, anomalies in these beam experiments can't be fully explained by three flavor models, fueling speculation about sterile neutrinos or exotic interactions. Yet the implications stretch beyond particle physics. If neutrinos oscillate differently under extreme gravity, say, near a black hole, it could distort supernova explosions in ways we've yet to model. Some cosmologists even suggest neutrino oscillations left an imprint on the large-scale structure of the universe, subtly guiding how galaxies clustered in the early cosmos. The enigma remains unsolved, but one thing's clear: neutrinos aren't just passive bystanders in the universe. They're active participants in a deeper, hidden dance, one that might rewrite the rules of reality itself. There's an invisible ocean filling every inch of the cosmos, not made of water or stars, but something far stranger: the vacuum itself. According to quantum physics, empty space isn't truly empty. It's a seething, bubbling soup of virtual particles that flicker in and out of existence, generating a background energy known as vacuum energy. This should be one of the most powerful forces in the universe, shaping the very fabric of space-time. But here's the problem: when physicists calculate how strong this energy ought to be based on quantum theory, the numbers are catastrophically wrong. The mismatch isn't just a small rounding error. It's a discrepancy of 120 orders of magnitude, a number so large it's like predicting a gentle breeze and instead measuring a hurricane capable of shredding galaxies. If the quantum field theories were correct, the vacuum energy should be so immense that the universe would have torn itself apart moments after the Big Bang. Yet here we are, in a cosmos where empty space exerts only a faint, barely detectable pressure. This glaring contradiction is known as the vacuum catastrophe, and it's one of the most baffling unsolved problems in physics. So where did our calculations go off the rails? One possibility is that we're missing a fundamental symmetry or cancellation mechanism in quantum field theory, some hidden mathematical balance that nullifies most of this energy. Think of it like two colossal waves in the quantum sea, perfectly out of phase, cancelling each other out to leave only a ripple. Supersymmetry, a popular but still unproven theory, posits that every particle has a superpartner with opposing quantum properties, potentially offsetting vacuum energy. But even if supersymmetry is real, it only reduces the discrepancy by a fraction. The gap remains unimaginably vast. Another radical idea is that vacuum energy isn't constant. It decays over time or varies across space. Imagine the early universe brimming with this energy, only for it to leak into extra dimensions or dissipate through some unknown quantum process. Some theories even suggest that vacuum energy and dark energy, the force accelerating cosmic expansion, might be linked, with the latter acting as a diluted remnant of the former. If true, the vacuum catastrophe wouldn't just be a theoretical hiccup, it could hold the key to understanding why the universe expands at all. Then there's the unsettling possibility that our most cherished theories are fundamentally flawed. Quantum mechanics and general relativity are the twin pillars of modern physics, but they clash violently when it comes to vacuum energy. Reconciling them might require rewriting the rules from the ground up, perhaps with string theory, loop quantum gravity, or something entirely new. The vacuum catastrophe isn't just a puzzle, it's a neon sign pointing to physics beyond our current understanding. For now, the mystery remains. Every experiment that confirms quantum field theory's predictions with stunning precision also deepens the paradox, as if the universe is teasing us with half-truths. Yet within this enigma lies an exhilarating opportunity. Solving the vacuum catastrophe wouldn't just patch a hole in our equations, it might reveal an entirely new layer of reality hidden in plain sight. And that's the thing about the cosmos. Its greatest secrets often lurk in the places we least expect, even in the empty spaces between the stars. What if gravity isn't a fundamental force at all, just a side effect, an illusion created by something far more primal? This is the bold claim at the heart of Eric Verland's emergent gravity theory, where the pull we feel between stars, planets, and even our own feet on the ground isn't woven into the universe's fabric but summoned into existence by chaos itself. At its core, the idea flips Newton and Einstein on their heads, suggesting gravity isn't a force to be quantified with equations. It's a cosmic mirage emerging from the relentless drive of entropy. Picture the universe as a vast, invisible quantum archive, a holographic hard drive where every particle, every interaction is information etched onto spacetime's boundary. Just as heat disperses in a steaming cup of coffee, Verland proposes that gravity arises from the universe's natural tendency toward disorder. When matter disturbs this informational soup, it creates gradients, regions where entropy must adjust to accommodate the new data. These adjustments, says Verland, manifest as what we perceive as gravity. It's like pressing your hand into a memory foam mattress. The foam doesn't pull your hand down. It reshapes itself unevenly, creating the illusion of attraction. The implications are staggering. First, emergent gravity neatly sidesteps one of physics' biggest headaches, unifying gravity with quantum mechanics. If gravity isn't a fundamental force but a statistical byproduct, there's no need to quantize it like the other forces. Second, it offers a fresh take on dark matter, the mysterious substance thought to glue galaxies together. Verlin's math suggests that what we've been calling dark matter might actually be the gravitational echo of entropy's hidden mechanics. Instead of invisible particles, galaxies could simply be responding to the way information is distributed in the unseen quantum substrate of space. Critics pounce on the theory's lack of experimental proof. Unlike general relativity, which predicted gravitational waves a century before we detected them, emergent gravity's predictions are harder to test. Yet tantalizing clues linger. Some galaxy rotation curves the speed at which stars orbit galactic centers align eerily well with Verlin's entropy-based calculations, no dark matter required. Even the infamous Pioneer anomaly, where distant spacecraft slowed slightly more than expected, might find an explanation here, as if entropy's subtle gradients were gently tugging at their trajectories. But the wildest twist, emergent gravity blurs the line between thermodynamics and spacetime. Black holes, long considered gravity's ultimate expression, become cosmic shredders where information and entropy collide. The event horizon isn't just a point of no return, it's a holographic screen maxing out its data storage, with gravity the error message spacetime generates when overloaded. If true, it would mean every falling apple, every orbiting moon, is just the universe doing its bookkeeping, settling its chaotic accounts in the only way it knows how. Whether Verlin's vision holds up or not, one thing's certain. It forces us to rethink gravity not as a force, but as a language, a dialect spoken between entropy and quantum information, echoing across the cosmic ledger. And that changes everything. What if our universe isn't expanding into some vast, infinite void, but is instead tucked inside the crushing depths of a black hole? This mind-warping idea, known as the black hole universe theory, suggests everything we know, every galaxy, every law of physics might just be the interior workings of a cosmic monster from a higher dimensional reality. Think of it like a Russian nesting doll of existence, where each layer hides another universe within its gravitational grasp. The math behind this is as elegant as it is unsettling. When a star collapses into a black hole, general relativity predicts its matter crushes down into a singularity, a point of infinite density where spacetime itself breaks down. But what if singularities aren't in points but gateways? Some solutions to Einstein's equations show that inside a black hole's event horizon, space and time switch roles. What we perceive as the expanding universe could be the stretched-out remains of that inversion. A big bang, not from nothing, but from the violent rebirth of infalling matter in a parent cosmos. Here's where it gets stranger. The properties of our universe, the speed of light, the strength of gravity, even the number of dimensions might not be arbitrary. They could be inherited traits shaped by the black hole that birthed us. Just as a whirlpool's spin determines how debris moves within it, the parent black hole's mass and rotation could set the fundamental constants of our reality. This might explain why our universe seems so finely tuned for complexity. Only black holes with the right parameters could spawn stable inner universes capable of harboring galaxies, let alone life. Clues might already be hiding in plain sight. The cosmic microwave background, the afterglow of the Big Bang, shows faint but puzzling anisotropies, patches of uneven temperature that defy standard explanations. Some theorists suggest these could be imprints of the black hole's structure, like shadows cast by the walls of our cosmic prison. Even dark energy, the mysterious force accelerating the universe's expansion, might trace back to the slow evaporation of our parent black hole via Hawking radiation, an outward pressure encoded as spacetime's stretching fabric. Not all physicists are convinced. Critics argue that black hole interiors are chaotic, turbulent places, hardly the nurseries for an orderly cosmos like ours. Others point out that the theory merely kicks the can down the road. If our universe lives inside a black hole, what spawned the black hole's parent universe? But proponents counter that this could solve the mystery of the Big Bang's origin. Instead of a singular, inexplicable event, the birth of our universe might be as natural as star formation, just one link in an infinite chain of cosmic nesting dolls. The wildest implication, if the theory holds, black holes aren't just celestial vacuum cleaners, they're cosmic wombs. Every time one forms in a higher dimensional universe, it might give rise to an entirely new space-time continuum inside it, complete with its own laws and constants. Our cosmos could be one of countless such offspring universes, each with physics subtly tweaked by its parent's properties. Some might be sterile, collapsing instantly, others could flourish with galaxies and life. In this view, the multiverse isn't just a theoretical playground, it's a fractal cascade of black holes birthing realities within realities. Whether the black hole universe theory is poetic metaphor or profound truth remains to be seen. But it forces us to confront a humbling possibility. The vast expanse we call home might be just the glittering interior of something far greater and far stranger than we ever imagined. Magnets are everywhere, from fridge decorations to the inner workings of your smartphone, and they all share one fundamental trait, a pair of inseparable opposites, a north and a south pole. Break a magnet in half and you don't isolate a single pole, you just create two new magnets, each with its own duo of north and south. But what if nature isn't so symmetrical? What if particles exist that carry just one magnetic charge, like an electric charge but for magnetism? These phantom particles, known as magnetic monopoles, aren't just a fun thought experiment, they're a missing puzzle piece in our understanding of the universe's deepest symmetries. The hunt for monopoles began with a stroke of genius from physicist Paul Dirac in 1931. He showed that if even one magnetic monopole existed somewhere in the cosmos, it would explain why electric charge comes in fixed, discrete units, an elegant solution to a mystery that had baffled scientists for decades. The math was so compelling that monopoles became a holy grail of particle physics, a ghostly signature of a universe more symmetrical than we'd ever imagined. But here's the catch: despite decades of searching, from deep underground labs to cosmic ray detectors, not a single definitive monopole has been found. So where are they? One theory traces their absence back to the Big Bang. In the searing heat of the early universe, monopoles should have been as plentiful as protons. Yet as the cosmos cooled, something may have intervened, a process called cosmic inflation, where space-time expanded faster than light, stretching their distribution so thin that finding one today would be like spotting a single grain of sand in a desert spanning billions of light years. Alternatively, monopoles might be hiding in plain sight, disguised as cosmic rays or trapped inside dense celestial objects like neutron stars, their magnetic signatures masked by unimaginably powerful fields. The stakes couldn't be higher. If monopoles exist, they'd rewrite electromagnetism, revealing a symmetry between electricity and magnetism so perfect it's almost poetic. They could also explain dark matter's gravitational grip or even hint at hidden dimensions curling through space-time. Some grand unified theories, which attempt to merge all fundamental forces, demand monopoles as a natural consequence, making their discovery potential proof that we're on the right track toward a theory of everything. Yet the longer the search goes on, the more tantalizing the possibilities become. Maybe monopoles aren't missing, just waiting for us to think outside the box. Recent experiments have proposed hunting for them not as free-floating particles, but as bound states in exotic materials or fleeting quantum fluctuations in powerful particle colliders. Others suggest looking for their cosmic fingerprints, anomalies in the universe's magnetic fields, or strange defects in the fabric of space-time itself. Whether monopoles are relics of a hotter, denser cosmos or figments of our mathematical imagination, Their absence speaks volumes. In physics, sometimes the most profound truths aren't just what we find, but what we can't. And that's the real magic of the monopole quest. It forces us to question not just the universe's answers, but the very questions we've been asking all along. At the heart of modern physics lies a glaring contradiction, one so fundamental it threatens to fracture our understanding of reality itself. On one hand, quantum mechanics governs the subatomic world with probabilistic precision, where particles blur into waves and existence hinges on observation. On the other, Einstein's general relativity paints spacetime as a smooth, bendable fabric warped by mass and energy. These twin pillars of physics work flawlessly in their respective domains, yet clash violently when forced to coexist. The result, a century-long quest for quantum gravity, the elusive theory that could stitch these disparate worlds into a single, coherent framework. But how do we hunt for something when we're not even sure what it looks like? The answer might be written in the faintest ink imaginable: the primordial patterns of the universe itself. Turn back the cosmic clock to the first slivers of time after the Big Bang, when the entire observable universe was compressed into a space smaller than an atom. Here, in this unimaginable density, quantum fluctuations and gravitational forces were inextricably linked, dancing on scales where spacetime itself may have been foamy and discontinuous. As the cosmos expanded, these quantum gravitational tremors stretched across the growing universe, potentially leaving behind cosmic fingerprints in the oldest light we can observe, the cosmic microwave background. Imagine the CMB as a fossilized ripple frozen in time, a snapshot of the infant cosmos where quantum gravity's whispers might still resonate. Some of the most promising signatures come from anomalies in the CMB's polarization patterns, the way its light waves vibrate in specific directions. Certain models of quantum gravity predict subtle spirals or swirls in this polarization, called B-modes, that couldn't arise from standard inflationary physics alone. These could be traces of primordial gravitational waves, not from cosmic inflation, but from spacetime's quantum nature asserting itself in the universe's first moments. It's like finding hieroglyphs in the static of an ancient radio transmission, a message encoded before the first stars flickered to life. Then there's the matter of spectral distortions, tiny deviations in the CMB's perfect blackbody spectrum. Quantum gravity models suggest spacetime's granularity at the Planck scale might have slightly heated photons as they traveled for billions of years, leaving minuscule imprints in their energy distribution. Projects like the Primordial Inflation Explorer aim to measure these distortions with unprecedented sensitivity, potentially uncovering evidence that spacetime isn't smooth but pixelated, like a digital image viewed from afar. But the real jackpot might lie beyond photons. Some theories predict that quantum gravity could have spawned ultralight particles called actions or even primordial black holes in the early universe. These exotic relics would weave through the cosmos like invisible threads, subtly warping galaxy clusters or creating lensing patterns that defy conventional explanations. The Euclid Space Telescope's high-resolution maps of dark matter distributions could inadvertently stumble upon these ghosts of quantum gravity, revealing fractures in Einstein's spacetime where quantum weirdness bleeds through. Of course, skeptics argue we're chasing shadows. The Planck satellite's painstaking CMB measurements found no conclusive evidence of quantum gravity's fingerprints, and alternative explanations, like interstellar dust or instrument noise, often muddy the waters. Yet the search is far from over. Next-generation observatories, from the Simons Observatory in Chile to space-based interferometers like LISA, will probe these signals with exponentially greater precision. What makes this hunt so thrilling isn't just the potential prize, it's the possibility of glimpsing reality's bedrock. Quantum gravity's signatures wouldn't just reconcile two theories, they'd reveal the universe's true scaffolding, showing whether spacetime emerges from entangled quantum bits, vibrates in higher dimensions, or folds into unexpected geometries. Every anomalous cold spot or curious polarization swirl brings us closer to answering a question that's haunted physics since Einstein. What breathes fire into the equations of existence? The early universe holds the key, we just need to learn its language. Imagine conducting an experiment where a particle's behavior changes depending on whether or not you're looking at it. This isn't science fiction, it's the unsettling reality of quantum mechanics, where particles exist in a haze of possibilities until measured, collapsing into a definite state only when observed. But here's the mind-bending question: what is observation? Does it require a human mind, a conscious being, or is any interaction with the environment enough? This is the heart of the consciousness-created reality theory, a controversial idea suggesting that reality itself might be sculpted by the act of perception, that the universe doesn't just exist but responds to the presence of awareness. The roots of this idea trace back to the infamous double-slit experiment, where particles like electrons behave as waves when unobserved, creating interference patterns on a detector screen. But the moment scientists install a device to measure which slit each electron passes through, the wave-like behavior vanishes and the particles act like tiny bullets. The act of measurement, of observation, seems to force nature to choose a state. Mainstream physics chalks this up to decoherence, where interactions with the environment collapse quantum superpositions. But a radical fringe proposes something far stranger. That consciousness itself is the missing ingredient, the trigger that crystallizes reality from the quantum fog. Proponents like physicist John von Neumann and Nobel laureate Eugene Wigner argued that the observer's mind plays an irreducible role in quantum mechanics. Wigner even devised a thought experiment, Wigner's Friend, where a scientist inside a lab observes a quantum event, while another outside remains unaware of the outcome. Until the outsider opens the door, the entire lab exists in a superposition, entangled with the observer's consciousness. It's as if reality branches based on who's looking, with consciousness acting as the knife that slices through possibilities, carving out the world we perceive. But what does consciousness even mean in this context? Skeptics argue that equating observation with human awareness is a category error, that a camera or a particle detector can observe just as effectively as a brain. Yet consciousness-centric theories counter that all measurement devices ultimately trace back to a conscious observer interpreting the data. Some interpretations, like the participatory anthropic principle, take this further, suggesting the universe requires observers to bring it into full existence. Without consciousness, reality remains an unplayed symphony of probabilities. The implications ripple beyond philosophy. If consciousness shapes reality, it might explain why the universe seems so finely tuned for life, a cosmic version of the "if a tree falls in the forest" conundrum. It also blurs the line between physics and metaphysics, raising the eerie possibility that minds aren't just passengers in the universe but co-creators. Experiments like delayed choice quantum erasers, where decisions made after a particle's journey seem to retroactively affect its past behavior, hint at a reality far more malleable than we ever imagined. Critics dismiss this as quantum mysticism, arguing there's no empirical evidence linking consciousness to wave-function collapse. They point to emergent theories where complexity, not consciousness, resolves quantum ambiguities. Yet the debate refuses to die, fueled by lingering gaps in our understanding of measurement. Perhaps the truth lies somewhere in between, a universe where consciousness doesn't create reality but dances with it, an inseparable partner in the unfolding cosmic story. One thing's certain, the mere possibility forces us to confront the profound interplay between mind and matter. Whether ultimate reality is shaped by thought or simply revealed by it, the question itself rewrites our role in the cosmos, not just as observers, but as participants in a universe still learning what it's allowed to be. What if the universe is younger than it appears, not because our measurements are wrong, but because it was designed to look ancient from the moment of its creation. This is the spine-tingling premise of the Anomalies hypothesis, a thought experiment that traces its roots back to 1857, when theologian Philip Henry Goss proposed that God might have created Earth with fake fossils, light from distant stars already in transit, and Adam with a belly button details suggesting a past that never actually happened. At first glance, it sounds like theological speculation, but resurrect this idea with a modern scientific lens, and it morphs into something far stranger, a philosophical grenade lobbed at our assumptions about time, evidence, and the very nature of reality. Think of it like a meticulously staged crime scene. Imagine waking up in a forest where every detail, the rings inside a fallen tree, the layers of sediment underfoot, even the light from a supernova 10,000 light-years away points to a history spanning millennia. But what if that forest was assembled yesterday, pre-aged to perfection? The Anomalies hypothesis suggests our universe could be that forest, its apparent age an elaborate illusion. Distant galaxies, pre-programmed light beams already en route, cosmic microwave background, a snapshot of a fictional Big Bang. Even your memories of last Tuesday might be part of the set dressing, implanted rather than experienced. Scientists recoil at this idea, not because it's disproven, but because it's unfalsifiable. If every piece of evidence for cosmic history could equally be read as part of an elaborate fabrication, how could we ever test it? Yet the hypothesis lingers like a ghost in the machine of cosmology, raising unsettling questions. Why does the universe look 13.8 billion years old if it isn't? Some secular interpretations flirt with simulation theory, suggesting an advanced civilization could have booted up our reality last Thursday, complete with pre-rendered memories of a deeper past. Others propose quantum retrocausality, future events influencing the present, as a mechanism that might backfill the illusion of age without divine intervention. The most chilling implication isn't about origins, but epistemology, how we know what we know. If reality can be convincingly staged, can we trust any empirical evidence? This paradox echoes in modern physics. Black holes may contain entire universes in their interiors, each with its own illusory past. Some interpretations of quantum mechanics suggest particles decide their histories only when observed, like actors improvising backstories mid-scene. Even the holographic principle hints that our 3D universe could be a projection from a 2D boundary where time behaves differently. Yet for all its provocations, the Anomalies hypothesis fails where science thrives: prediction. It doesn't offer new phenomena to observe or mechanisms to test. It merely casts doubt on existing ones. Still, it serves a vital purpose. Like Descartes' evil demon or Boltzmann's brain, it's a philosophical stress test probing the limits of what we call knowledge. Whether divine prank or glitch in the cosmic matrix, it forces us to ask, if the universe is lying about its age, how would we ever know? And more hauntingly, would it matter? After all, an illusion consistent enough to fool every instrument, every experiment, every memory becomes indistinguishable from truth. In the end, the universe's greatest hidden pattern might not be in its structure, but in the story it tells about itself. From the Fibonacci spirals hidden in galaxies to the holographic code that might underpin reality, these 30 theories aren't just curiosities, they're seismic tremors rattling the foundations of what we call real. Consider how quantum entanglement defies distance, linking particles across the cosmos faster than light. Ponder the Boltzmann Brain paradox, where your very consciousness could be a fleeting accident in the void. Marvel at the possibility that black holes might birth entire universes inside their crushing depths, or that the zodiacal lights glow once guided civilizations toward truths we're only now rediscovering. Each of these ideas peels back another layer of the cosmic onion, revealing a universe far stranger, more interconnected, and more mysterious than we ever imagined. Think of the axis of evil in the cosmic microwave background. an unexplained alignment that hints at a lopsided universe, or the eerie precision of the golden ratio echoing from sunflowers to solar systems. Remember phantom energy lurking in the equations capable of shredding spacetime itself. And what about the octonions, those 8-dimensional numbers that might be the universe's secret language? These aren't just abstract musings, they're clues scattered across the cosmos, waiting for us to piece them together. Here's the wildest part: these theories don't just challenge science, they rewrite our place in the story. Are we accidental specks in a chaotic void, or participants in a grand cosmic symphony? Is reality a simulation, a hologram, or something beyond our current comprehension? The more we uncover, the clearer it becomes. The universe isn't just stranger than we think, it's stranger than we can think. Now it's your turn. Which of these theories blew your mind the most? Was it the idea of white holes spewing out matter like cosmic fountains? Or the chilling notion that we might be Boltzmann brains, hallucinating reality into existence? Drop your favorites in the comments. Let's geek out over the possibilities together. And if you're hungry for more mysteries, hit subscribe. The cosmos has endless secrets left to reveal, and we're just getting started. The universe isn't done surprising us, and neither are we.